All right, so let's get it started here. So yesterday we started to talk about the fixed axis rotation, and we drive the Newtonian equations for fixed axis rotation. It was like something, if we have like a circular body, something like that, and this body is pinned at this location. Like let's assume that there is a pin here, and this is, as we know, this is the center of mass of the circle. And there's multiple forces acting on this body, like we have F1 and F2, and maybe a moment here, and F3 at this location. And we have the weight of this body is going down. To solve any problem, we need to draw a free body diagram and kinetic diagram. So I will go ahead and draw another circle and put all the forces on this body. So you might assume that I have all the forces from the first figure here, but actually it's missing something. So let's see what is missing. So we have F3, F1, F2, and we have a moment, and we have a weight, but we are missing the forces at the pin here, because this pin has some reactions. It restrains the motion in the x and y direction, or in the tangent and normal direction. So there is some reaction at this pin. Let's like assume that you have a pin and you hold one of the ends of this pin from the end, and you try to pull this pin from your other hand. So there's some reaction will be induced on the other end of the pin. So this is what happened here at the support. And if we are working with Cartesian coordinate system, so we will be having like, for example, we will have fx in this direction, and fy, you might call it rx or ry. So there's some reaction at this point. So don't forget to put these reactions. So this is the free body diagram. And the next thing is the kinetic diagram. So let's assume that this is our circle. And for the kinetic diagram, we will search for the center of mass, which I assume will be here. And for fixed axis rotation, this body will allow to, like, for example, let's say it will allow to move in the tangent and normal direction. So to know where is the tangent and normal direction with respect to this point, let's assume this point O, and we have the pin here. So I will stretch a line from G to O. So this is point O and this is point G. And as we know that the normal direction will be always going in this direction from G to O. So this is, we will have MAN, and we will assume that this body is going to rotate in this direction. So the alpha will be in this direction. So here I will have MA tangent, and I will have the last thing, which is the alpha. So I will have I bar alpha, something like that. Okay, so this is how to map the acceleration on this body and how to draw the free body diagram and kinetic diagram. And actually, we did the last time on a general body here. So we put all the forces and we stretched the line from the O to G and identified the MA tangent and MA normal. So what will happen if this body was bent at the center of mass? Like, we assume that there is a pin here. If there's a pin here, so the center of mass will not have a tangent or a normal. So it will be the MA tangent at the center of mass. So let's put a bar here, will be equal to 0. And this body will only allow to rotate about this point. And we will have only I bar alpha. So this is if we have a disk, or we have a body that's bent at the center of mass. Okay, so let's write the Newtonian equations. So as we know, if we are working with rigid body, we will have 3 Newtonian equations. We will have the sum of the forces in the tangent direction, and it will be equal MA tangent of the center of mass, and this is a vector equation. And as we know, the A tangent knowing alpha will be equal to M, and this will be equal to the alpha crossed by RG with respect to O. Okay, so, and if you want to know RG with respect to O, so there's point O and there's point G, so you will stretch a vector here, and this will be RG with respect to O. And you know the direction of alpha, so right now we have, this is RG with respect to O, and from the right-hand rule, you will know that alpha will be positive direction. So it's something like, okay, let's make it 3D here. So this point O, and this is RG with respect to O. So here's O and here's G. And if you use the right-hand rule, you will find that alpha is going outside the plane like this. So this is alpha because we have alpha is something like that. And if you crossed alpha by the RG with respect to O, it will give you something in the plane like this. So let's make it in a different color here. So this is perpendicular to G and alpha, and this is the direction of the A tangent. So this term, and that's rational because you will have the MA tangent is going this way. Something like that. Okay, so this is for the F tangent, and for F normal, it will be equal M multiplied by A normal at the center of mass. And as we know that this is equal to omega square dot product negative RG with respect to O. So this is F tangent and F normal. And if this body is pinned at the center of mass, so the A tangent and the A normal at the center of mass will be equal to 0. So this 2 will be equal to 0. Okay, so let's go to the third equation, which is sum of the moments at the center of mass will be equal to I bar alpha. So we get the moment of all of these forces and all of these moments and make them equal to I bar multiplied by alpha. And we proved last time if it's better for you to get the moment about point O, so it will be I about O multiplied by alpha. And we proved this last time, and here's the proof. We get MO and it's equal RGO, RG with respect to O multiplied by this, and moved forward to prove that MO will be equal to IO multiplied by alpha. And actually this rule is true for fixed axis rotation at the point of fixed axis. So true at the point of fixed axis rotation. And the point of fixed axis rotation, actually, it's an instantaneous center of zero velocity. So this point O is an instantaneous center of zero velocity, or we can call it a permanent center of zero velocity because the velocity will be equal to 0 at this point. So this rule is true for instantaneous center of zero velocity as well. True for instantaneous center of zero velocity. You can call it ICZV. Right, so let's solve a problem on this concept. So for this example, we have a bar. And when you have a bar, you will go to your dynamic equations and see what is the IXX and IYY of this bar, or you determine what you need from the dynamics sheet. Okay, so right now we have a bar. The mass of this bar is 20 kilograms and it's a slender rod. So we can use the slender rod equation. Has an angular velocity omega equal to 5 radian per second. And determine the angular acceleration and the horizontal and vertical components of reactions of the bin here. So needs the reactions here. Okay, so first you will have to determine at which axis this rod is moving. As we know from the dynamics sheet, okay, let's put this up there. You will find that there is something like this, and you have the y-axis is something like that. So this is y, and this is x, and this is z. So this body, we will have x-axis is coming out of the plane here, so it's rotating about x-axis, so I will be using ix. So when I use iz, if this bar, like this, and you are given in your problem that this bar is under torsion, like there's some twisting on this body, something like that. So that means that this body is rotating about z-axis, so I will be using iz. But in my problem, the body is rotating about x-axis, so I will be using ixx. So this is the ixx. And if I want to get IO, it's completely different from the I at the G. So I know that this is the center of mass of the body, and this is IO. It's different from, and you are given in the dynamic sheet, both the I at the center of mass at the end and at the end of the bar. Okay, so let's see how can we solve this problem. So what I will do, I will apply my three equations, this three up there. This is for any problems, any Newtonian problems. I apply this three equations, and you can apply them with any order you want. So let's like mix the order from the bottom to top. So I will have sum of the moment MO will be equal to IO multiplied by alpha, and I need to determine a positive direction to use it in my problem. But before you do this, so that you can get the moment and you can get the I node and alpha direction, you will have to draw a free body diagram and kinetic diagram. So this is the free body diagram, and I will put my kinetic diagram here. In the free body diagram, you will have to put all the forces on this body. So let's put all the forces on this body. The only one that I can see is that we have a moment here equal to 60 Newton meter. So Newton is a kind of force, so we include it in the free body diagram. And this is the center of mass, so I know that there is a weight is coming down from here. And don't forget the reaction. So this is the bend point, and I will assume the direction of the reaction. So I will assume that we have Fx in this direction and Fy in this direction. You can call it F tangent and F normal, whatever you would like. And in the kinetic, so this is the free body diagram. And let's draw the kinetic diagram. For the kinetic diagram, I will only put the axes. So I have, let's assume that this is x-axis and this is y-axis. And you can call it tangent normal. Okay, y-axis. And I will put the directions of the accelerations. So I will assume, actually the body is moving in this way, so I will assume that the MA tangent is this way, and we know if this is point O and this is the center of mass, so this is the fixed axis rotation point, so I will have MA normal is in this direction, and I will assume that this body has an I alpha in this direction. So I put the right-hand side of the Newtonian equations in the kinetic diagram and the left-hand side on the free body diagram. Okay, so let's solve the problem. So let's get the moment about point O. So this is point O, and I get the moment about point O because it's much more simpler. It will eliminate two unknowns, Fx and Fy. So getting the moment about point O, knowing that this is the positive direction, so the 60 Newton meter will be in negative direction. So I will have negative 60. And the weight is also doing a negative moment. So the weight will be like, I know that the mass is 20 kilogram. So this will be 20 multiplied by 9.81. So this is the weight. And we multiply the weight by the moment arm, which will be 1.5 meter, given that this is 3 meter. So this will be 1.5. Okay, the I node, so you will go to dynamics, to the dynamics sheet, and you will find that the I at the end of the bar is equal 1/3 ml squared. So this will be equal to 1/3 multiplied by 20 multiplied by the L of the bar 3 squared multiplied by alpha. So from this, I will be able to get alpha. And so let's see what is the direction of the alpha before I put the alpha. So I assume that this is the positive direction of the rotation. It's clockwise, but here in my problem, I alpha is actually in the same direction. So I will put it here. So it will be positive alpha like this. And finally, we will get that alpha will be equal to negative 5.905, which means that the alpha is in opposite direction that I assumed. Although that the omega is the, okay, so the omega is in this direction. So alpha is in direction with the omega. That means that this body is accelerating. So it's alpha and it will be radian per second square, and it should be in opposite direction than the assumed one. Okay, so this is I get alpha from the MO. So let's move to another equation. So we can move to the sum of F in the, we can call this a normal direction. So we can say Fn, and or you can say it X, whatever you want. So sum of forces in the n direction will be equal MAN. So the forces in the n direction or x-axis, the only force that we have here is the Fx. And let's assume that the positive direction is in this direction. So the Fx is in negative direction. So I will put negative Fx. And negative Fx will be equal to the mass multiplied by A normal, and A normal will be omega square multiplied by negative RG with respect to O. So let's see, this is the magnitude of RG with respect to O, and it's in this direction. So if it's a negative, it will be in this direction. And this is our positive direction. So this will be equal to negative Fx will be equal to the mass 20 kilograms multiplied by 5 radian per second square multiplied by R, which is 1.5 meter, but let's be careful about the direction. So negative multiplied by RG with respect to O, it's equal negative 1.5 because this is in this direction and this is our positive direction. So negative multiplied by negative will give you a positive direction. So Fx will be equal to a negative 750 Newton. So we got Fx. So let's apply our last equation. The sum of the forces in the tangent direction will be equal MA tangent. And we will have the forces in the tangent direction. We have Fy is, so let's assume the positive is going down. So Fy is going up, so it will be negative Fy. The W is going down, so it will be positive W, which is 20 multiplied by 9.81. Okay. The left on the right-hand side, so we have MA tangent assumed down. So this is positive mass, the mass is 20, and A tangent is equal to alpha crossed by RG with respect to O. Okay, so right now we have, this is the direction of RG with respect to O, and alpha is assumed is in this direction. So if using the right-hand rule, it will give you that alpha, this is the alpha direction. Multiplying your alpha by your the RG with respect to O, it will give you something like this. and this will be the direction, and this will be in a negative direction. So we will have 20 multiplied by, let's make sure that we have everything right here. So we have, oh, I multiplied alpha by RGO, so it will be something, assume that this is, let's make it a 3D here. We have a bar, and this bar is rotating, actually. Okay, so the alpha is rotating something like this. So that means that when you crossed alpha, actually, it will should go up. So the A tangent here should go up. So just like this is confusing. Like, let's make this alpha I node alpha, something like that. And if you know that alpha is in this direction, that means that the A tangent at this point, or at this point, it will be going up. So this will be equal to negative, because it's an opposite sign than this. So we will have negative alpha, and alpha, we got alpha from there. So negative multiplied by negative. So let's negative multiplied by negative 5.905. And this will be multiplied by RG with respect to O, which is 1.5. So what I did, I multiplied that alpha and R in a like a magnitude and got the directions using the right hand rule. Or you can put them as a vector and multiply this vector like I and J or N and T. But usually it's much more easier for me is to get the directions directly from the right hand rule and multiply the magnitude separately. And this is a single equation function in Fy, and Fy will be equal to 19.05 Newton. So it's as simple as you draw the free body diagram and the kinetic diagram, and you have only 3 equations. And what you will do, you will get the left-hand side of this equations from the free body diagram, and you will get the right-hand side from the kinetic diagrams. And be careful about the directions and about the cross products. Okay, does anybody have any question about this problem? Okay, so I will move with I'll give some introduction about the general plane motion. Okay, for general plane motion, let's assume general plane motion is something, so we know how the translation look like and how the fixed axis rotation. So if we have circular disc or a bicycle wheel moving on the ground, something like that, and this wheel having like an alpha is in this direction. So this wheel is moving in this direction. So what it's doing is it's rotate and translate. So at some point, this wheel will be here. So what it did, the center of mass moved it from here to here and also keep rotating. So this is a general plane translation. And as we know, that is this is an instantaneous center of zero velocity. And our equations will be something like the sum of fx will be equal to the max of the center of mass, and the sum of fy will be equal to may of the center of mass, and also the sum of the moment about the center of mass will be equal to I bar alpha, or you can use the sum of the moments about any point B. Like if you want to get the moment about this point P, it will be equal to I bar alpha plus RG with respect to B crossed by MA vector, and A should have an X and Y components. So this is if a Cartesian coordinate system. If you are working with a tangent normal coordinate system, so the xy will be transformed to tangent and normal. And a special case, if you are taking the moment, if B is an instantaneous center of zero velocity, so you can have the I at the instantaneous center of zero velocity and multiply it by alpha. So if you are taking the moment here at this point, so you can get the I at point O and then transform with the barrel theorem axes the I at this point. And I think in the dynamics sheet, you are given both the I at the G and the I at the any edge of the circle. And you can use it directly and multiply it by alpha. And usually this point is a very special point because it has the normal force and it has the friction force. So taking the moment about this point will eliminate many unknowns and make your problem easier. But if you take the moment about G, you will have F and N. You will like reach the same answer, but it will give you much more unknowns to solve with. And when the number of unknowns increase in the verse, so your probability to make mistakes, it will be much more higher. So if your equations is much more easier, so the problem will be a little bit easier. So I think there isn't much time to solve a problem. So okay, so on Monday I might like start to solve some problems, like 2 or 3 problems on the rigid body in Newtonian kinetics for general plane motion, and finish this chapter. Does anybody have any questions on the general plane motion or rigid body translation? Okay, so this, I think you guys are good to go to start your quiz.
Thank you.
Thanks.
Professor, I missed a part of the lecture. Could you go up on the on what you had just written?
Okay, just like let me stop the